Hello dear EAPCET aspirants, welcome back to NEET World. So in this session we will be discussing general organic chemistry and particularly application of inductive effect, and after that we will be discussing mesomeric effect. Okay, so these are the two things we are going to do in this session now along with the PYQs, and let's understand the application of inductive effect using previous year questions. Okay, both I will be considering both JEE questions, NEET questions as well as EAPCET questions. Okay, so particularly we will be covering more number of EAPCET questions. Okay, right. So if you are new to this channel, just click on the like button before starting the session and you can watch complete video. Okay, right. So here just let me check whether voice is clear or not. Right. So here see, in the last class I have explained about inductive effect and its classification. Okay, now we will be seeing its applications of inductive effect. Okay, along with that we will be seeing resonance effect, that is what mesomeric effect we can study. Okay, right. So I hope you remember that there are two types of inductive effect. One is plus I effect, other one is minus I effect. So how we are classifying them? Depending upon the polarization, depending upon type of groups attached to the carbon chain. If this is our carbon chain, so to this carbon chain, if a group G is attached, that group G is having ability to release the electrons into the chain through this sigma bond, then we can say that group G as plus I group. What I am saying? Plus I group. See, if this G group is having ability to release the electrons into the carbon chain, we are saying it as a plus I group. Okay, so what are the plus I groups we have? See, any species, the group may be any of the species or any species having more electron density on it, whether it is electronegative, electropositive. If it is having negative charge on it, what I am saying, group G having negative charge on it act as electron releasing group. What is a group considered as electron releasing group? Since it has more electron density, now that electron density is shared to this carbon chain through this sigma bond, specifically mentioning that through this sigma bond. Okay, so those effects are called plus I effect. See here, these are the groups. See, nitrogen atom is more electronegative atom, that is fine, but it has negative charge now. So whenever it is having negative charge, that group definitely act as a releasing group. Okay, plus I group. Okay, now in the same way, see, if we have a carbon chain like this, so in the first case, if group G is something like O minus, and in the second case, if this group G is sum of any of these groups, see, let us say I am taking this a group here attached here. Okay, like this we have a group here. So now what happens? In which case more inductive effect, more releasing nature can be seen. See, when a group G is this side, towards this side, more negative charge on it, that will be more readily give the electrons. It means a carbocation is placed over here. So this is also third carbon content positive charge, but here G I am saying O minus. Now O minus can releases electrons more easily and that can stabilizes this carbocation. Okay, when I compare with this isopropyl group, so group G, if it is O minus, that will be more stabilizing this carbocation by releasing the electrons, because O minus is having more electron density now. So that negative charged electrons comes into the chain more effectively through sigma bond when I compare with this isopropyl group. Okay, so this is what the inductive effect order you need to remember. See, now I will be showing you some questions based on this to make you more clear with the concept. Just patiently listen for next 20 minutes, definitely you are going to feel more confident on this GOC part. Okay, especially inductive effect applications. Okay, right. Now look at this. Minus I groups are there. So these are the minus I group. If the hydrocarbon chain, the carbon chain having any of these elements, I mean any of these species, I am indicating that with a G dash. G dash can be any of these. Okay, so now any of this group is attached here to the carbon chain, then that group will drag the electrons towards itself. Then we can say it is electron withdrawing group. What I am saying, electron withdrawing group or simply -I group. Okay, so now which group will be having more ability to drag the electrons towards itself can be considered strong, that group as strong electron withdrawing group. Out of this, see, Nr3 is having more -I in nature. See, Nr3 plus on it. So more electronegative atoms with positive charges strongly withdraw the electrons. What I am saying, more electronegative atoms with positive charge. See, electronegative atom means generally it is more tendency to gain the electron, but these fellows are having positive charges on them. Right now, if they have positive charges, their electron withdrawing nature will be enhanced, it will become more, therefore they have more tendency to drag the bonded electrons. For example, let me show you this chain. Like this I am writing here positive charge, on this carbon we have one NO2 group, and one more thing I am writing C, okay, and here I am writing cyanide and positive charge on this carbon. Now tell me which carbon cation will be less stable here. See, both of them are electron deficient, but this is stronger -I group when I compare with the CN. Right now, if this is a stronger -I group, what it will do, it withdraws the electrons towards itself more effectively when I compare with this cyanide. Therefore, what happens here, so it will be destabilized more when I compare with the cyanide. Okay, so out of this AB, which is more stable now, see, it is more destabilized by this NO2 group now, therefore it will be less stable when I compare with B. So I can say A is less stable than B. So this is how you will get the order of this stability in case of carbocations and also in case of carbon anions, okay, depending upon the groups attached and the order of their effect. Okay, so you need to remember this experimental order to solve the questions properly. Okay, and it is very easy to remember. See, nitrogen with more positive charge will be act as strong -I group. Okay, these are nitro group, cyanide group, these are what, less when I compare with Nr3 groups. Okay, right, and let us solve some questions here. Look at these questions here. These are from EAPCET paper. See, here we have a carbon having positive charge on it, which is having two alkyl groups right now, and here we have only one alkyl group. Okay, so now what we know, if more the number of alkyl groups, more will be the releasing ability of that alkyl groups. Right now, so here only one alkyl group, here two alkyl groups. So one side only it is donated, but here two alkyl groups, so 2 +A groups you can say. Okay, 2 +A groups, and the stability of these alkyl groups will be more properly explained using hyperconjugation. We will study in the upcoming session, but as of now you remember, more +A groups, more will be the stability of this carbocation. Okay, so out of this 3 and 4, I can say 3 is more stable than 4. Okay, 3 is more stable than 4. Okay, and after these two things, no, you can see option 5 and option 2. Okay, see, these carbons are sp3 carbons, 3 sigma, like 3 bonds, 1 sigma and 2 pi bonds are there. So this sp carbons, this is what, 2 bonds are there, means this is sp2 carbons. Right now these are sp2 carbons, these are sp carbons, whereas this is sp3, this is sp2. Okay, so now sp, more s character, more percentage of s character, more is the electronegativity. What I am saying, more percentage of s character, more will be the electronegativity. See, if that electronegativity is more, having positive charge on it makes it to be unstable. Therefore, this fifth one is highly unstable when I compare with the second one. Second one is highly unstable when I compare with the fourth one. Therefore, I can say here least stability is for 5 and here 2. Okay, like this we can arrange. Now the final one we have here is first one. So this is benzylic carbocation, which can be properly explained, its stability is properly explained through conjugation, that is what mesomeric effect I can say here. See, this is like this, CH2 place. Now this carbon is stabilized by conjugation of these pi electrons. Okay, so that is what benzylic carbocation stabilization. Okay, now where do we have 1 is more stable, 1 is more stable than 3, 3 is more stable than 2, 4, 2, 5. So option 1 will be a perfect answer for the question. Okay, right. So any confusions are there in this explanation? I hope no confusions. I hope there is no confusion here. Yes guys, if there is any confusion, feel free to express in the chat box. I will definitely answer it. Yeah. Yeah, let me give you few more questions. There are a lot of questions actually here to discuss. Once we discuss complete 3 effects, then you will answer them more effectively. That's what I am looking for. See, correct order of stability of this reactive intermediates they are asking. So here also how can you answer this? See, here we have CH3 group, one alkyl group is plus I group. Okay, and this one CH3 O CH2 plus is there. Yes. What about this group? You just tell me here. So now this carbocation can be stabilized by mesomeric effect of this oxygen lone pair electrons. So this is how it will be stabilized. Yes, this is perfectly correct, because mesomeric effect is more dominating than inductive effect and hyperconjugation. See here you have carbon sp2 carbons with positive charge. Okay, and this carbon is sp3 carbon with positive charge. Now this positive charged carbon is called allylic carbocation, can be stabilized by this pi electrons delocalization. So but here we have carbon with positive charge which is sp2 carbon. Right now this is sp2 carbon. So sp2 carbon means you should say it as a vinylic carbocation. So there is no conjugation for this, but here we have a conjugation like this. So this is more stable. Yes, this is correct, this is also correct. Okay, like this we need to arrange. And here see we have a negative charge, carbon with negative charge, carbon with negative charge. So now what kind of groups stabilizes the carbon anions? See here we have nitro group, this is minus I group and minus M group, and here alkyl group is there, this is plus I group. So just tell me, already they have negative charges on them. Now negative charge is stabilized by withdrawing them towards themselves, right? See, this negative charge will be more stabilized, negatively charged carbon, that is carbon anion, will be more stabilized when that negative charge is drawn into the ring. So here nitro group is there now, so this is withdrawing group, electron withdrawing group. So it will withdraw the negative charge and makes it to be more stable when I compare with this. Okay, because it is a plus I group now. So what these plus I groups do? They will release the electrons into the system. Already it has negative charge. Now again this alkyl group is releasing group. Now what happens? It will destabilizes the system. So it is less stable when I compare with this. So this is also correct. Now they are asking which are the following correctly represents the stability of reactive intermediate. Yes, all these are correctly represents as of now. And look at here, you have 3 alpha hydrogens to stabilize this, then this one. Okay, and this one is how many are there? So 3 here, 6, and 3 alkyl groups now. So here 2. So total 6 plus 2, 9, 6 plus 2, 8 alpha hydrogens are there to stabilize this carbocation, whereas this carbocation has only 3 alpha hydrogens, which is less stable. So it means this is incorrectly matched one. Okay, fourth one is incorrectly matched. So you can say 1, 2, 3 will be a perfectly arranged based on their stabilities. Okay, this is what you need to solve. Okay, yes, let us discuss few more questions, and before discussing few more questions of this GOC part, let me explain you mesomeric effect so that you will solve the questions with more confidence. Okay, so this question in the last class I have given it as a homework. So how can you solve this? Tell me. Very easy now. See, we have acidic carboxylic acidic groups here, carboxylic acid groups are there, but fluorine is there, chlorine is there. What we know, fluorine, like fluorine is more electronegative atom, so therefore minus I effect of fluorine is more than chlorine, right? Now minus I effect of fluorine is more than chlorine, therefore it will withdraws the electrons towards itself more effectively when I compare with fluorine withdraws the electrons more effectively when compared with this chlorine due to its more minus I effect. Now due to that minus I nature, the carboxylic acidic nature will be increased whenever there is electron withdrawing groups on carboxylic acids. The carboxylic acid acidic nature increases because after releasing H plus ion, it will be forming conjugate base like this, okay, CH2 and some group G here, F is there. So this negative charge is more stabilized when this group G is more stronger withdrawing group, okay. So this group G is more stronger withdrawing group, that will increases the conjugate like that will increases the stability of this conjugate base. Therefore I can say option 3 will be more acidic, then 2 and least one is A, 1, that's it. This will be your answer for the question, okay. Hope this is clear. Now let us discuss mesomeric effect first, okay. Let me give you the clarity on this mesomeric effect. Okay, so look at this, mesomeric effect means this is the effect will be observed due to delocalized system. This will be observed in delocalization system or delocalization containing systems. What do we mean by delocalization? See, it will be of different types, like it can be pi, sigma, pi, okay. So delocalization of pi electrons, I can say delocalization of pi electrons in this case, okay. So delocalization of pi electrons, like pi electrons with pi bonds, okay, or pi bonds with carbocation, or pi bonds with carbon anion, okay, pi bonds with vacant orbital, like this different types of pi electron delocalization is present. So finally what we are seeing, the pi electrons will be delocalized their position, or they will be shifting into the other positions, then we can say them as delocalization. See, for example, here CH2 double bond CH, single bond CH, double bond CH2, like this there. See, pi bond, sigma bond, pi bond, right now. So pi bond, sigma bond, pi bond. So this kind of system now have possibility to undergo delocalization. How it will be? See, these pi electrons will shift here and these pi electrons will shift onto this carbon, okay. So that you will get a structure like CH2, single bond CH, double bond CH, single bond CH2, negative charge, like this, okay. So now what you have seen, this pi bond is shifting from here to here. So this carbon is losing the pi bonded electrons now, so it should get a positive charge in it, okay. And it is shifting here like this, then this is shifting here. See, the pi bond is purely shifting onto, completely shifting onto this terminal carbon now. So carbon with a negative charge. Like this, you need to draw the delocalization structures. Now what is the other possible delocalization? I told you pi bond, alternate like sigma bond, and the next positive charge, okay. So how can you write these? CH2 double bond CH, single bond CH, positive charge, like this I am writing. Now this pi bond can shift into the vacant orbital of, vacant p orbital of this carbon, so that you will get CH2 plus CH double bond CH2. See, this pi bond is shifted into the vacant p orbital of this carbon, which is carbocation, so forming this kind of conjugation. So 1 and 2, okay. Hope this is clear without having any confusions. So now this kind of systems are called allylic systems. What I am saying? Allylic system. Now you might be getting a doubt that, sir, is this possible or not? CH2 double bond CH, positive charge here. See, these are not in conjugative positions now, so it means this pi bond cannot be shifted anyway, okay. So there is no conjugation here, there is no conjugation anymore in this. So this kind of systems are called vinylic systems. What is that? Vinylic If it is carbocation, vinylic carbocation. This is allylic carbocation, like that. Okay. If there is negative charge, allylic carbon anion. This is vinylic carbon anion. Yes, allylic carbon anion also, if I want to take, yes, let us write that CH2 double bond CH, CH2 negative charge, pi bond, sigma bond, negative charge. So negative charge shifts here and this pi bond becomes a negative charge. Okay, negative charge becoming pi bond becoming negative charge here. So CH2 negative, sigma bond CH, double bond CH2, like this. Okay, this is structure 1, this is structure 2. Okay, so these are the two possible resonating structures for allylic carbon anion, you can say. Okay, hope this is also clear without having any confusions. Okay, so let's move forward with few things here. Yeah. So now, so this inductive effect is of two types. Mesomeric effect is of two types now. Due to that conjugations, mesomeric effect is of two types. See, to the carbon chain that conjugate to the conjugated system. Now, how many types of conjugated systems we have seen? Pi, sigma, pi, one type. Pi, sigma, negative charge, another type. Pi, sigma, positive charge, one more type. Like that, we have different types of conjugative systems now. So now see, pi, sigma, pi, like this I am writing, this pi, sigma, pi, like this we can write. And here you just see here what I am writing here, see what I am writing here, to this system, to this conjugative system, I am attaching a group G. Okay, if this group G is any of these compounds, any of these things here which I have mentioned. Okay, so now what they are seeing having commonly, see they have lone pair non-bonding electrons in common for all of this right now. So if this group G having non-bonding electrons, that is what lone pair electrons, that will be donated into this carbon chain like this. Okay, now when it is donated, it will be shifts here. Okay, and this carbon is getting negative charge. Again that negative charge can be donated here and this pi bond will shift over here. So now what you are seeing into this chain, carbon chain, you are releasing electrons. What you are releasing? You are releasing electrons. So that this group G is called electron releasing group. What is that? Electron releasing group. If there is a group G which is having non-bonding electron in it, which is releasing electrons into the hydrocarbon chain or into the system whatever we are considering, then we can say that that particular hydrocarbon chain and G as electron releasing group, and that is ring activating or like chain activating group here. Okay, so now what it is doing, it is releasing into the ring now, I mean into this chain now, so you can call it as electron releasing group, and effect is called plus M effect. What is that effect? Plus M effect. The common thing about all this group is listed is here is having atom connected with conjugated system has a lone pair electrons to donate. So it means you can observe this more effectively here. Just see here, I am writing a ring which is conjugated. I can say it as a benzene ring simply, which is having OH group now. See, OH group is having lone pair on it, that can be donated into the system like this. Right now, if it is donated, what is happening here? Just check here. OH, negative charge here, like this we are saying. Okay, again this negative charge is given here and it is becoming like this now. See, you are seeing in the system, you are seeing a negative charge right now. So what I can say, this ring is activated by the groups something like this. So these groups can be any of that group having lone pair on it. Okay, so that can be donated, lone pairs can be donated into the ring and activating the ring. Okay, having negative charges right now. So we can say them as a ring activating groups. Okay, so now what you are seeing in the ring, the negative charge is increased, electron density is increased due to the presence of this OH group. Okay, so we can say electron releasing groups increases electron density in the ring. Now where do you seeing this negative charges? See, on benzene ring, if any of the group is attached, adjacent position to that group is called ortho positions. What is that group? Ortho positions. Okay, what is that positions called? Ortho positions. And I can say 1, 2, 3, 4, 5, 6. Okay, so now here 2, 6 positions are called ortho with respect to group G. And here odd numbers you can remember 3 and 5 are called meta positions. What is that? Meta. And this fourth position is called para. Okay, so where you are seeing the negative charges, you have seen the negative charges ortho, and one more is a para. If I want to write one more resonating structure like this, you will be now seeing again at ortho positions only, but not at a meta. Like this only we have, see, again at ortho only we have got that negative charge. So it means this electron releasing groups in mesomeric effect increases electron density at ortho and para positions of this benzene substituted compounds, okay, on this phenyl ring. Like this, see, you have seen negative charge at ortho, para, and again at ortho. So I hope you got that electron releasing groups in mesomeric effect activate the ring or increases electron density at ortho and para positions, but there is no mesomeric effect at meta position. Very, very important statement it is. Okay, mesomeric effect is not observed at meta position, you can remember this. Okay, similarly, now there are some groups, and again let us take a benzene ring. Okay, to this I am adding group G, that is any of this thing. Okay, let us say nitro group is attached. Okay, this nitro group, what it will be doing is, it will only drag the electrons towards itself from the ring. But here if you see in the previous case, what happened, that group G is donated electrons into the ring, but it is accepting or withdrawing electrons towards itself now. So therefore I can say all these groups as electron withdrawing groups. What is that? Electron withdrawing groups. Now once again we will see what happens in case of electron withdrawing groups. Very easy, just observe over here, you will get complete clarity. See, nitro group means you write the structure properly like this. Okay, see the pi electrons, see here pi electrons of this nitrogen oxygen is there, which is more electronic to oxygen, right? It will take the pi electrons. Okay, it will take the so now what happens, this pi electrons is taken towards oxygen, that creates a positive charge on this nitrogen, right now. Therefore to balance that positive charge on the nitrogen, the pi electrons from the ring is donated here. So now what happens, tell me, see here what is happening here, nitrogen with a day 2 bond with oxygen, this side is becoming O minus. Okay, so now this nitrogen is getting positive charge, therefore what happens is, this ring pi electrons are shifted here, therefore the positive charge is removed from this electronegative oxygen atom. Okay, atom, and here you can write a pi bond and a positive charge over here. Okay, so now carbon having positive charge, what is the position, this carbon position is now ortho position now with respect to this adjacent position means ortho. So ortho position with a positive charge, again it will be shifts here. Like this, again where you have seen this positive charge at a para position, 1/4 position right now. And is there any other way here? Yes, see here you can write this shifting here and positive charge, making positive charge over here. Okay, like this. So what are the positions you are seeing positive charges? Ortho positions and a para position. It means what you got finally. So inductive effect decreases, this mesomeric effect. Which mesomeric effect? Minus M effect here. Okay, electron withdrawing group containing cyclic compounds, conjugated systems, these electrons will be moved towards electron withdrawing group side only. That is what mesomeric effect says here. So any of this group. Okay, now what happens? The electron density in the ring decreases and creates positive charges at ortho and para position, particularly in case of benzene ring. Okay, phenyl ring you can remember. Okay, so it means electron density will be at very low at what positions? Ortho and para in case of electron withdrawing group. Okay, if it is electron releasing groups, so the electron ring activating groups makes a negative charge at ortho and para. So both effects, plus M, minus M, both will be seen at ortho and para positions only, no effect at meta position with respect to this mesomeric effect. Remember this statement. Okay, right. So now, sir, you have we have discussed this very effectively, but what is the use of knowing this? Just look at here. This is the application of inductive mesomeric effect. So what it is says, arrange the following in the order of decreasing order of their acidic strength. So it means which is more acidic, which is least acidic, we need to identify here. See here, out of this, let me explain few things first. Let me explain very few things before explaining this complete question. We have OH, and here NO2 group, here OH, CH3 group. Okay, out of these three compounds, which is more acidic, they will ask. How can we solve this? Very easy, very easy. Just look at here. Acidic nature of these phenols depend upon their conjugate base stability. If this phenol is releasing H+, acidic nature means releasing of ability to release H+ ion. If this H+ ion is released, now what is the conjugate base formed? O-, phenoxide ion. So this is also forming respective phenoxide ion after releasing H+, NO2, and this is also forming phenoxide ion after releasing H+. These are the three things formed here, A, B, C, if you compare. Okay, so but which phenoxide ion is more stable here? Tell me. See, which is more stable? Which is more stable? See, this negative charge will be effectively dragging towards the ring when we have an electron withdrawing group like this. Okay, so negative charge must be shared between more number of atoms, therefore its stability increases right now, because negative charge means high electron density. Whenever there is high electron density like negative charge, that must be shared. If there is electron deficiency, whenever we are seeing carbocation case, that positive charge must be stabilized by giving electrons to that carbon. Okay, it means cation positive charge means electron releasing group must be present, negative charge means electron withdrawing groups must be present for stability. Okay, so here negative charge is there and electron withdrawing group is present here. So electron withdrawing group stabilizes this negative charge. So we can say, so B will be more effectively stabilized when compared with A and C. Okay, now between A and C, which is more stabilized? See, here there is no such groups, but here you have releasing group. See, no group, releasing group, withdrawing group. See, whenever there is electron releasing group, so these electron releasing groups releases electrons into the system, and here already negative charge is there. We require a group that should withdraw this negative charge, but this is releasing now, so that will further destabilizes the phenoxide ion here. So I can say electron releasing group containing phenols are less acidic. So this is least acidic, C is least acidic. When it comes to this, there is no releasing group, withdrawing group means definitely it will be intermediate between B and C. So you can make two statements perfectly here. So acidic nature of organic acids, I am saying acidic nature of organic acids increased by electron withdrawing groups. Okay, if any electron withdrawing groups is attached, the acidic nature of that organic compound will be increased. Okay, and electron releasing group containing organic acids show less acidic nature, or electron releasing groups decreases the acidic nature of organic acids. So it is electron releasing groups, it will be having no least acidic, so C is least. So simply identify which type of groups are attached. If it is electron withdrawing group, so it will be having maximum acidic nature, releasing group minimum acidic nature, no group intermediate acidic nature, that's it. This will be the perfect way of understanding the concept. Okay, now we'll be giving you few questions. Just tell me here. Look at this, the stability of the following alkoxide ions. This is from JEE Mains. How can you answer me? Tell me fast. How can you answer this? Very easy. Yes, anyone can try. Anyone can try and give me your answer for this. Yeah. So look at this. The correct order of stability of the following alkoxide ion. Very easy. See, negative charge system is there, like oxygen with a negative charge. So we can say alkyl group, oxygen, negative charge. This is called alkoxide ions. Okay. So now the negative charge species will be stabilized by electron withdrawing groups. What is it? Electron withdrawing groups. Nitro group, nitro group, nitro group. All of them are withdrawing groups only. Perfectly fine. Now, how can we answer this? More the number of conjugations, more is the stability. What I am saying? More the number of conjugation, delocalization. See, this will be delocalized here, negative charge comes here, and this negative charge again go into the nitro system, right now. So, like that we have maximum number of conjugations here. See here, this conjugation is with respect to this double bond. So, here only one conjugation we are seeing, right now. And here there is no such type of conjugation only. Okay, so it means where do we have maximum number of conjugations? Yes, here you have maximum number of conjugation. And also if there is any cross conjugation system, see this double bond is also in conjugation with this nitro group also. It means this is only stabilizing it partial amount, not complete amount. So it means where do we have more number of conjugation? C. After C there is no conjugation only, there is no possible conjugation. Here at least some amount of conjugation is possible. Therefore, C more stable than B and least stability is for A. What they are asking? Correct order of stability of the following compounds. Maximum is for C, B, A. So, option 2. Okay. I hope discussion is clear on this. If these discussions are clear, just click on the like button first. Okay. Click on the like button. And you can express your concerns in the chat box about the discussion. Okay. Next. See, anything like any discussion, any topic here you have doubts or confusions, please mention in the chat box. We will definitely discuss those things. And you know, whatever the concerns you have or whatever the doubts you have, just post in our Telegram group. We will be definitely look into it and we will solve them in the upcoming sessions. For example, in your college or in your institute, you are unable to follow some particular topics of JEE, NEET or EAPCET, just post it in our Telegram group or in our WhatsApp group. That links for those things are given in the description box. Okay. So definitely we will be solving them either in the short video formats like short videos or in the upcoming live sessions. Okay, so this is one of the best way so the like to communicate with us regarding your conceptual understanding, okay, or conceptual learning. Okay, the next thing here, in the same way, can you answer me this, which are the following carbocations is less stable? Okay, less stable. Again, this is also related to conjugation only now. See, carbocations are there. Stability of carbocations again explained by this conjugation. This is also one application of mesomeric effect. But again I am saying that about cross conjugation. See, this positive charge can be donated here, we will get a positive charge here, and this can be stabilized by donation of these pi electrons. So you will get a positive charge here, that can be stabilized by this lone pair electrons. Okay, it's a perfectly in conjugation system. So 1, again 2, this is 3. But here if you see, one positive charge here, one time it is delocalized, again this is second time, this is 2 times, this is 3 times, let us say, and this will be stabilized here one time, and the next this one 2 times. Okay, and this is not perfectly stabilizing because it is in conjugation with this pi electrons and lone pairs. Okay, it is like having some cross conjugation, little amount of cross conjugation, therefore 3 is more stabilized than 2, you can say. And here this positive charge will be stabilized by this pi bond electrons partially, because why I am saying partially, it is having conjugation, these pi electrons are having conjugation with this lone pair electrons, but not with this carbocation, with this lone pair. So it means the least stability is for A 1, and the next 2, and next 3, and more stable is 4. So which is more stable here? As per the question, fourth option will be your answer. This is complete explanation of the question. Okay, right. Next thing, basic nature of amines can also be explained by mesomeric effect. Especially basic nature of aromatic amines is properly explained using this mesomeric effect. So how it will be, see for example, I have nitrogen atom with lone pairs on it. So we can say this is aniline. Okay, now here I am writing a group that is electron releasing group. Okay, so now one more compound will write NH2 electron withdrawing group. Now tell me which compound is having more basic nature. What I am asking? Basic nature. Okay, so basic nature means what? There will be one H plus ion. Okay, so that H plus ion is readily acceptable. So which of these will accept this H plus ion more readily? Therefore, if this is accepting H plus ion more readily, I can say this is more basic. Okay, like that, which is more basic they will ask. Very simple. See, if these lone pair electrons are very free to accept this H plus ion, then we can say it is more basic. See, if this lone pair electron density is more here, if someone is pushing from back side, then that will be easily accepting this H plus ion. Right now, see what type of group here we have? Withdrawing group. So it will withdraw electrons from the ring, as well as the lone pair electrons nitrogen also dragging towards the ring, towards this electron withdrawing group side. If it is like this, the availability of this lone pairs to accept this H plus ion is very less. So I can say electron withdrawing group containing amines are less basic. So I can say C is less basic. Okay, now if we compare between these two, here releasing group is there now. So this releasing groups releases electrons into the system, and that makes these lone pair electrons electron density more effective to accept this H plus ion. So activate the ring by releasing the electrons into the system, that makes the like nitrogen to donate electrons to accept a H plus ion. So I can say amine with electron releasing group increases its basic nature. Electron releasing group containing amines are more basic. So B here, and there is no such group releasing withdrawing, so it will be in between them. Okay, B, A, C will be your answer. So hope the discussion is clear. Based on this, can you answer me this EAPCET question? Yes, you can easily try this. So what is your answer for this? See here, nitrogen lone pairs, here also lone pairs are there. So what type of group this is? Methoxy groups, alkoxy groups are releasing groups as per mesomeric effect, plus M effect. Okay, and this is nitro group, this is minus M effect. So if it is minus M effect, these lone pairs are completely in conjugation and that will be taken towards the electron withdrawing group side only. So now these lone pair electrons are less available to accept this H plus ion, therefore this will be least basic, C is least basic. Between A and B, see these lone pair electrons are not in conjugation with the ring like an aliphatic amine, this is aliphatic amine, this is aromatic amine. Okay, so now these lone pairs are not in conjugation means these are very readily available to the accept this H plus ion. So B is highly basic when I compare with the other options. Okay, because in A the lone pair electrons are in conjugation whereas in B not in conjugation. Okay, and in C it is in conjugation along with this ring, it is in conjugation with this nitro group, that's why this is least basic because less available, this lone pair electrons are less available to accept this H plus ion. So what I can say, C is least basic, then A, and highly basic is B, that's BAC will be your answer for the question. So option B will be your answer for this particular question. Okay, right. Okay, next. So can you answer me this question? Acidic nature of phenols. So very easy, we already discussed on this. See, nitro group is withdrawing group at para position, this is withdrawing group at meta position, this is releasing group at para position, and there is no such group. We know releasing groups, electron releasing groups decreases acidic nature, So it means 2 will be least acidic. Okay, there is no group, means no group is here, and here withdrawing group, definitely withdrawing groups means more acidic than normal without any groups or releasing groups. So up to here it is clear, and between these we know para position have mesomeric effect minus M effect, but there is no such effect at meta position, only inductive effect is seen, minus I effect is seen. So I can say para position, so it will be more stabilized, conjugate base is more stabilized, so this will be more acidic. So you can write 4 and in between 3, like this you need to answer the question. Okay. Okay, so where do we have that kind of option here? 4, 3, 1, 2. So B, option B is your answer for the question. Okay, right. Can you answer me this one question as the same as the previous discussion? Just tell me your answer in the comment box for this particular question. Okay, and next, see, look at these carboxylic acids. So tell me their acidic nature. What I told you, carboxylic acids, like any organic acid, its acidic nature will be more or increased when it has strong electron withdrawing group. See, we have cyanide, we have fluorine, and we have NO2, which is effective minus I group here, minus M group here, so nitro group. So this is effective minus M group, strong minus M group, so that will makes it to be more acidic, carboxylic acid to be more acidic. So C is more acidic. Then next, between carboxylic cyanide and nitro is more minus M effect, the next cyanide, therefore A will be more acidic, and this is weakly deactivating the ring now, so I can say B here. So C, A, B, second option. Option B will be your answer for the question. Okay, right. And the next, see, it will also affect on bond length. What I am saying, it will also affect on bond length. See, we know single bond length is more than double bond, I mean partial double bond and complete double bond and complete triple bond. See, whenever there is conjugation, what happens? For example, if there is a carbon nitrogen system like this, I am writing it like this is the system, okay, CH2, if you want you can balance there, okay, this is the system. Now I am writing here bond length A, and one more thing, you just see here what I am doing, NH2 CH NO2 nitro group I am adding here. So now I am saying this is bond length A, this is bond length B. So what will be the relation between A and B? If A is greater than B or B is greater than A, AB are equal, or how it will be? This is how a question can be made here. See, whenever these lone pairs are in conjugation, yes, see, these lone pairs are in conjugation, yes, here also in conjugation, okay, here also in conjugation. So when they are participating in conjugation, what is happening to the single bond? It is converting into double bond right now. So it means a CH2 CH double bond NH2, this is positive charge here, negative charge here, right. So this kind of conjugation is taking place. Due to the conjugation, this single bond becoming double bond. So I can say this carbon nitrogen will be having now partial double bond character due to the conjugation here, okay. And here also you have such a type of conjugation, and you know the conjugation is more effective here because that lone pair electrons are more effectively dragging towards this electron withdrawing group right now. So it means if these lone pairs are dragging towards this side, this single bond becoming double bond here more effectively when I compare with this. Therefore, more double bond character will be seen in the second case when I compare with the first case. So double bond character is more for B than C. Therefore, if more double bond character, if more partial double bond character, its bond length is less, okay. So I can say single bond length is more than partial double bond character. So both of them are having partial double bond character, but double bond character is more in B, therefore bond length is less in B when I compare with A. So this is what bond length order, okay. So bond length is inversely proportional to bond order. So more double bond character or more bond order, less bond length, okay. Based on that we can solve this type of questions, okay. Hope the discussion of this topic is clear. Now just tell me what will be your answer for this particular question. Here they are saying by giving two compounds here, this aniline with aldehydic functional group and here nitro group as a functional group, they are saying this bond length as X, this as Y. What is the relation between X and Y? Which is more, which is less? How can you answer that? Tell me. Again it is very simple. The lone pair electrons of nitrogens are in conjugation here, yes, here also in conjugation, but this is aldehydic group, this is nitro group. So what we know, nitro group is more minus I group, minus M group, that will withdraws the electrons more effectively towards itself. So it makes this double bond, this nitrogen lone pairs in conjugation with the ring as well as this nitro group more effectively now. So this will be now converted into more double bonded, I mean more effective conjugation, that makes it to be having more double bond character. So if more double bond character than this, so its bond length will be less because bond length inversely proportional to bond order. So more double bond character here, so bond length will be less in Y. So I can say X is greater than Y, that's it. This will be your bond length order, okay. This kind of questions we can see in the exam, okay, in especially JEE mains, okay, right. Can you answer me this question? Okay, let me give you one more question for that. Okay, this question take it as a homework and tell me what's your answer in the comment box. I wanted to know acidic nature of these 5 compounds which I have mentioned here, and along with that you can also say basic nature of these amines. What will be your answer for this? See, JEE mains question very easy. If you are unable to solve, no worries, I will explain in the next session, okay. And in the next session we will be discussing about hyperconjugation also. If you know answer about this particular hyperconjugation based question, just tell me answer for this, that in the comment box. Okay, and next here one more question from EAPCET, and this question is also for you, and this question is also for you, this question is also for you. All these are for you to practice. Okay, so just try them. If you are unable to solve them, just attend the next live sessions or mention the question number in the chat box. Will definitely give you the answer for that. Okay, so hope you enjoyed this session. So thank you for watching. Stay connected with our NEET World YouTube channel. Thank you.